This is chapter 5, part 2 from slide 18. So we're going to review likelihood ratio tests. Now, likelihood ratio tests apply to nested hypotheses, and here's what it means to be a nested hypothesis. So the whole parameter space is some capital theta, which we're going to suppose is a subset of Rd because it's a d-dimensional parameter. And we have two nested hypotheses, H0, which is theta is in theta 0, and H1 is theta is in theta 1. And these are going to be nested parameter subspaces with dimension d0 and d1. And d0 is going to be less than d1. d1 has to be less than or equal to d. And theta 0, therefore, theta 0 is going to be required to be a subset of theta 1. Now, when you have a hypothesis, you have a maximum likelihood corresponding to the hypothesis when you constrain theta to be in the appropriate parameter space. So in the context of ARMA models, right, then you could, D would be the largest ARMA model you're thinking of. So if you have ARMA PQ, then D would be P plus Q plus 1 for the noise parameter sigma squared. And then as you start considering submodels that have P and Q smaller, then D would be correspondingly smaller. Now, we come to the Wilks approximation, which is under the null hypothesis theta 0. So if the smaller model is true, then L1 minus L0, that's the increase in the log likelihood from adding an extra parameter, is roughly half chi-squared d1 minus d0. And this approximately equal sign here means is approximately distributed as. I call this Wilks approximation rather than Wilks theorem, because basically Wilks theorem says that this approximation is true in some asymptotic limits, but often it's a good approximation in finite samples too. It's a likelihood ratio test because a difference of log likelihoods is a ratio of likelihoods. And right, so I guess I've said the last 2 points already. It's a sort of deep and useful result. It's slightly surprising result, really, because it doesn't depend on the form of the model particularly. It just says, you know, whatever your model, at least if Wilks theorem applies, then you have this nice limit, and it lets you talk about whether the extra increase in the likelihood from adding a parameter is sufficiently small that it could be perfectly well explained by the smaller model being right. Now, there's a close relationship between likelihood ratio tests and profile likelihood confidence intervals. There's always a duality between hypothesis tests and confidence intervals. And so that if the estimated parameter theta star does not lead us to reject a null hypothesis, then that's the same thing as saying that theta 0 is in the 95% confidence interval for theta. And let's see what the 95% cutoff for a chi-square distribution with 1 degree of freedom is. It's 3.84. According to the Wilks approximation, we have to divide 3.84 by 2 to get the likelihood cutoff. So we get this 1.92 that we saw before for the profile likelihood. Now, here's another method that we mentioned before, Akaike's information criterion. So likelihood ratio tests are useful for nested models, and they're useful when we want to test a formal hypothesis. What do you do when the models are not nested? And a very common technique is this AIC, which compares likelihoods of different models by penalizing the likelihood of each model by a measure of its complexity, which here is penalizing by twice the number of parameters in the formula. AIC is minus twice the maximized log likelihood plus twice the number of parameters. And we're trying to minimize AIC. So the plus 2D is then a penalty. And AIC was derived as an approach to minimizing prediction error. And the reason why that's a very similar goal to model estimation is that if you add unnecessary parameters to your prediction rule, then you get, in fact, poorer prediction from overfitting, which decreases the predictive skill of the fitted model in out of sample. And so Akaike went ahead and worked out in some asymptotic limit what the right penalty was to balance out that overfitting. And that's where AIC comes from. AIC is all well and good, but it's a little bit of a trap that you may feel tempted to use it for more than it is. So viewed as a hypothesis test, AIC may have weak statistical properties, and AIC was never intended to be a hypothesis test. And so you have to remember not to interpret AIC by making a claim that the favored model has been shown to provide a superior explanation of the data at a test of some size. But if you don't try to take it for more than it is, viewed as a way to select a model with reasonable predictive skill from a range of possibilities, it's often useful. So I'm sure you'll be using it in this course. Here's a little calculation to compare AIC with likelihood ratio tests, right? They both compare differences of the log likelihood, so they're really very similar. Suppose the Wilks approximation is valid, and consider the strategy of selecting the model with lowest AIC. View this as a model selection approach as a formal statistical test. You can ask, what is the size of this test? And that's a sort of algebraic thing. So let's go do that. Well, Wilks's result says that the log likelihood on the larger space minus the log likelihood on the smaller space is approximately distributed as chi-squared on degrees of freedom equal to the dimension of the larger space minus the dimension of the smaller space with a half out here. Right? And then if we just write out how that relates to AIC, the AIC difference between model 0 and 1 is then the difference of AIC the difference of AIC. AIC is minus twice the log likelihood plus twice the degrees of freedom. So that's twice L1 minus L0 minus twice D1 minus D0 so Wilks Wilks would have you say that if I take delta AIC and I multiply it by 1/2, and I add d1 minus d0, then I get that this is approximately 1/2 chi-squared d1 minus d0. And in the one-dimensional case, I get, according, in this limit, the probability that the difference of AIC is less than 0, which is the chance that you reject that null hypothesis, is then, well, depending on which way you do the difference, you okay, this is the increase in the AIC. So this is then the probability that chi-squared 1 is less than 2, which you can calculate in hang on, this is the probability that chi-squared 1 is less than 1, which in R is p chi-square 1 on 1 degree of freedom, which, let me just calculate that. P chi-square 1 on 1 degree of freedom, which is 0.68. Okay, so we see that an AIC is much less stringent a test than a likelihood ratio test. Okay, and next we're going to move on to likelihood-based inference for ARMA models in R, and let's get started on it in this segment. So we're going to do this through a data analysis of the depth of Lake Huron. And of course, here we are in Michigan. The Great Lakes, an important resource for leisure, agriculture, industry. Now, management of the Great Lakes is something we have responsibility for. Human activities such as water diversion or channel dredging could lead to a decline in lake levels. And alternatively, currently in recent years, there have been high levels that could lead, or that have led, to coastal erosion. And you can wonder whether the lake levels are driven by climate change. Are we going to have additional problems in future of the lake level going up? Or possibly diverting water out could be leading to lake levels dropping, which could be another problem. In principle, global climate change could lead to lake levels dropping too. The physical mechanisms are not always obvious. For example, the main evaporation season from the Great Lakes is not the summer when it's hot. It's when you have winter days that are cold, but the lake is not ice covered. And then the air is dry, and so the water evaporates quickly. Anyway, so we want to look at the data, and so we can find monthly time series data on the depth of Lake Huron. The data's on the course website Here we just have the structure of the data in the file. It's a comma-separated file with date in this particular format. Now, when we want to do data analysis, we're going to have to manipulate the date variable a little bit. This is a fairly common way for date to be represented in a data file, but we want to get it into a numeric format. And a standard format is something called POSIX-CT, the number of seconds since the beginning of 1970 as a signed real number, and the R function strp time maps various formats into this standard POSIX-CT format, and then you can extract whatever you need from that. And you can look at the R help on date time classes for if you find yourself wanting to deal with any other related kind of date issue. Anyway, here is an example of how to do it in this particular case. So I've read in the data, and I've applied this strp time, and then I've extracted out the year and the month, and you can see what we get. We now have a data set where the year and month can be analyzed separately. Later on in the course, we're going to get into seasonality in time series, but we're not doing that right now. So we're going to avoid monthly seasonal variation by considering an annual series of January dates. And so here we go. I've extracted out the Januaries and plotted them, and you can kind of see what's going on. It looks like there was this kind of fairly long-term decline in depth, and then stabilized. Perhaps it's been declining a little bit more, and these data only run to 2016, so you can't see the more recent uptick. We are going to be fitting ARMA models. Right now, we're not looking at trend. We're just going to fit a stationary ARMA PQ model under the null hypothesis that there's no trend. And this hypothesis is not entirely unreasonable looking at this data. So there might be a trend, but remember how just when we were looking at white noise earlier on this semester, you could have white noise that looked quite like there might be some trend there. So it's easy for your eyes to kid you. It's reasonable to at least evaluate the possibility that there's no trend, just chance variation. And so we're going to fit a stationary Gaussian ARMA PQ model, and we're going to fit a mean mu. And so the model looks like this. Phi of b applied to yn minus mu is psi of b epsilon n. This is now the standard ARMA model, so there's not so much to be said about it. Mu is the expected value of yn in this model. Phi of x is the AR polynomial, psi of x is the MA polynomial, and the epsilon is IID normal 0 sigma squared. We need to decide what values of P and Q to use, and here's one way to do that. We can try very quickly with a computer a whole range of values of P and Q and tabulate the results in an AIC table. Here's some code to do it. I don't think I'll say that much about it. You can figure it out by yourself if you want to. Let's go straight on to what it looks like. Here we have the ARP on the rows and the MAQ on the columns. And so, well, what do we learn from this table? Well, I guess the first thing to do is to identify the model with the lowest AIC, which I guess is going to be this one here. The lowest AIC corresponds to ARMA. P is 2 and Q is 1. And it's also useful to note roughly where the reasonable models are. There's a white noise model, ARMA 00, is clearly kind of ridiculous for this. But if you look in some sort of cloud around here, you have various nearby models have AIC within a few units of ARMA 2.1. And remember that AIC is essentially in log likelihood units, and so 1 unit is the substantial thing. It doesn't matter whether the AIC has value 2000 or 20 or 200. Still increasing it by 1 or decreasing it by 1 is the thing that has the statistical meaning. Just looking at this, what looks like the second best model, perhaps it's this. So let's say that's AR10. Is also a competitive model. Which is simpler. Of course, AIC already accounts for simplicity. So looking at it as simplicity as even an advantage once you've already accounted for it is potentially problematic. But the bottom line is that AIC is not very punitive for complexity. And so just looking at this model, it seems reasonable to take the ARMA 10 model quite seriously. Okay, when you're doing AIC, you have to be careful not to overinterpret the results of the table. And so let's practice writing something for that. Well, here's, I guess, one new consideration we haven't seen before, which is that AIC comparisons, like any model comparisons, in fact, any numerical model comparisons, cannot tell us if all the models are bad. Right, all it can say is that one model is a little bit better than the other, one model is much better than the other, but that doesn't, just because it's the best of a bad set of models wouldn't make it a good model. We could look at say time plots of residuals would be one way to help look at that. Looking for outliers or other patterns in the residuals. And then, of course, always with AIC, also, as we already mentioned, we must be careful not to interpret AIC as if it were a formal hypothesis test. Okay, great. And we'll carry on this data analysis in part 3.